Welcome to our presentation of Lab 7, all about counters. Our group members include Sebrin Billings, a software engineering major from Dallas, Texas, who is stress baking her way through the end of the semester. Kevin Billings, also from Dallas, a software engineering major benefiting from my stress baking, and Sarah Reese from Salt Lake City, also a software engineering major. First, we will review using K-maps and minimized equations. Next, we will declare our thesis. Then, we will examine 3 types of counters. Following that, we will present the circuits built in Logisim. And finally, we will relate our conclusion. Let's review. With don't cares, you can include them to simplify or leave them out if they are useless. Also, the loops determine the equation based on which variables within the loop do not change. In the example on the right, set 0 is a loop with 2 squares. Beginning in the top square and moving down, you can see that the only value that changes is C. The green loop with 1 square cannot be minimized. In the red loop, the only value that changes is B, so drop it out of the equation and you are left with the values that did not change in the loop. Now that you have a minimized equation from your K-map, how do you use it? The equation gets translated directly to gate logic, telling you which outputs to use for each input. In this graphic, you can see that a wire is branched off the output of B and brought around to be used as an input on the flip-flops. Since the equation calls for B and B naught, both outputs will be used. Now we'll flip over to Sarah.
Why, thank you, Sebrin. As you know, counters are an important part of the architecture of a digital systems. They are used to facilitate memory storage, compute unique system states, also known as CUSS, create time, or most importantly, keep track of video game high scores. Now to Kevin, we're counting on you.
Thanks, Sarah. Counters allow us to apply time to digital circuits. In these cases, the circuit says change X when state Y occurs. An example of this would be an alarm clock or a timer on a camera shutter. This lab covered 1, 2, 3 types of counters: the up counter, ring counter, and gray code counters. Now we'll pass it back to Sebrin.
Thanks, Kev. First, let's look at up counters. Remember when we said that counters allow us to apply time to our circuits? Notice the transition table to the right and the current outputs or current state of our Logisim circuit. The current output matches the values for Q2, Q1, and Q0. Based on our transition table, we expect that our next state will be N2, N1, and N0. Observe how the only external input is the clock, with the outputs from each flip-flop making up the remaining inputs. Now let's look at another type of counter.
Ring counters. Let's say you've got a video surveillance system and want to save some hard drive space. You decide to only keep 1 out of 5 frames of the video. A ring counter could be used to tell the computer to save a frame, skip, 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 and save a frame again. You'll notice that the ring counter circuit will not function properly until the reset signal is received. This was a pitfall that I faced as I created my circuit and started reconsidering my life choices when the clock button did absolutely nothing. The key was understanding that the counter in our lab did not start at 000 like some of the previous counters did. It starts at 000 is in an invalid state. The ring counter starts at 001 anytime the reset signal was received. Now Sarah will explain the next counter.
Now let's discuss gray counters. The gray counter is also on a rising edge clock, but as the transition table on the right shows, it is counting in gray code. Again, this is often used in memory because it is more power efficient. The reason for this is because it takes less power to transition between one change in the cues. For example, the transition between 0, 1 and 1, 1 is less dramatic than transition from 0, 1 to 1, 0. As we consider this, it makes sense that the logic used for memory storage, which is possibly the most common process for a computer, is power efficient, because that would elongate the life of batteries in things like laptops, cell phones, and tablets.
Without counters, computers would only be capable of existing in a current state, either on or off, and would be limited to a single function. With them, the computer can progress through sequential future states and remember necessary data to perform increasingly complex tasks. Thank you for your time and good luck on your exam this week.